Let's get the recording going here. And any questions before I just start in with a field theory? I'm gonna do the simplest field theory first, and then we'll build up. And I'm hoping one of these blue markers will actually work. Almost. Yeah, the problem with the black markers, I know those show up the best, but all right, well, they're almost there. They leave such crud on your board, and they're very messy. I don't know why they should be worse than anything else, but they are. So what we want to do is just apply the same procedures that we have applied to. Is that noise in the background a problem? You guys hear okay? Okay, all right. Yeah, there's something rattling across the house here. So our dynamical variables in classical mechanics, quantizing a particle are, say, the position and the momentum as functions of time. So the way to think about what we're doing, all right, these become operators. The way to think about what we're doing is, just imagine that we have more parameters sitting inside. So a field now has 4 parameters instead of 1. Now, this parameter is not the same as that dynamical variable, and that can cause confusion. So just don't get confused. We've just got a bunch of parameters here. So when we take if we take a time derivative of x, here on phi, we would be taking space-time derivatives. So we have more derivatives around. And notice instead of a total derivative here, it becomes a partial derivative there. Now, the other thing that changes is that we're looking at, well, say a wave operator. So let's see, you guys have done some field theory. So a massless scalar field, massless Klein-Gordon type field. We could write the wave equation this way, and we can write that in a variety of ways. We can use the Minkowski metric here on a couple of partial derivatives. The action for such a field, a half is just a convenience, and then we might put a minus sign if we want it to come out positive, but essentially we're just looking at something like this. Okay, familiar so far? Everybody good? Then if I vary this, I vary the action and set that to 0, then I have a minus a half here. I'm going to get 2 of the same thing here because this really is a symmetric thing. This is d mu, or no, let's write it d mu phi, d nu phi with an eta mu nu. So you can write this in a nicely symmetric way so that you see that you really just get a factor of 2. You're going to cancel that, and then you have d mu phi, d mu times the variation of phi. And now you integrate by parts and require the variation to vanish on the boundary of whatever region you're talking about. And that's going to get rid of the minus sign. And you end up with d mu phi times del phi. And so setting this, demanding that that be 0 for arbitrary variations phi, means that this thing, which is just the del inversion of phi, is 0. Okay, everybody cool with this? Yeah, you're good. Okay, great. So that's a massless Klein-Gordon field, if you like. Now, I've written that as an action. It can be viewed as a Lagrangian, as the integral of a Lagrangian. So if I write L dt, then what is L? Well, the Lagrangian is the integral of, let's put the minus a half out front just so I don't have to keep writing it, is d mu phi d3x. So the Lagrangian becomes a functional, right? You give me a whole function phi, I can tell you what the Lagrangian is, if I can integrate well enough. So this L is actually a functional of the field phi and its derivatives. Okay, so what that means is where before we might have looked at how L changes with respect to the velocities and defined that to be the conjugate momentum. Well, that's the same thing, but now taking a partial of L with respect to something like phi dot, it's really a functional derivative. So properly speaking, what we want is the variation, the first functional derivative of L with respect to phi dot. Now, you know, this doesn't usually make any difference. You're pretty much looking at the same thing. It's pretty much like a partial derivative because the functionals we're dealing with are simple quadratic things, not complicated functions where you have to really use the formal definition of a functional derivative and do these one parameter things. The gauge theory book has a formal definition of a functional derivative. So if you need it, there it is. For these, not so much. Let's see. Oh, I clarify in the notes that d0 is 1 over c ddt. So, and we call that ddx0, just a notational thing. So we're not writing the speed of light all the time, but it's in there, and if we have to put it back, we can. So this this sum we write as d mu phi, and we know what that is. Now, there's a notational thing in field theory, just because it comes up now and then, not that infrequently, that you want a Euclidean inner product of 4 things. So I can take d alpha phi, and if I want a Euclidean inner product, well, okay, I could take a d beta and use a Euclidean inverse metric here. We don't do that. Well, you can, but we write both indices down. So sometimes we'll run into notation where it's convenient to take the sum over all 4 coordinates instead of the Lorentzian inner product. This is not Lorentz invariant, right? It's, you know, the sum of ddt squared and the Laplacian, not the difference. So it's a different thing, but it comes up as you know, part of the number of expressions. And you know, despite the abhorrence of such things to those of us with relativity training, yeah, you know, all right, fine. Now, let me see.
Professor?
Yeah.
Can you go into a small summary as to how we're able to separate the time and the spatial components from this like action and Lagrangian? I mean, I know it can be done, but I would just want to hear the explanation at least once in my life. Stay
in Minkowski space, right? You know, we're not doing curved space-time here, so we can pick a time. You know, pick some inertial reference frame and, you know, use time in that frame. if you've got to be much more careful if you work with these things in a curved spacetime. You can do, and people have written books on quantum field theory in curved spacetime. Hartle and Hawking showed in the 70s that if you do a path integral where you're varying the metric as well as everything else, you're trying to quantize everything, that the corrections due to fluctuations in the metric only come in at second order. So first order quantum field theory can be done on a fixed spacetime background. And if you have a time-like killing field, then you have an idea of what direction time goes, and you can work from that. It's more complicated, but in such situations you can do it. Now, if you start looking at fluctuations of the metric, straightforward canonical quantization of general relativity is beset with problems of gauge. All right, your coordinate choice is really gauge freedom, and you've got a huge gauge group with the symmetries. And the one thing that really muddies the treatment of canonical quantization really does come down to time. The fact that one of your parameters is coming in with the wrong sign makes it very hard to define your space of states. So one of the things you're going to see us doing is defining a vacuum state, raising and lowering operators that add quanta to the vacuum, AX, and produce multi-particle states. And that way you can apply arbitrary numbers of arbitrary raising operators to produce arbitrary numbers of particles in your flat spacetime. But that's hard to do in relativity, because the thing you would want to put on the right side of your commutation relations is the Minkowski, the Lorentz metric, and it's got a minus sign in it. So your states are not going to be, you're not going to have a positive definite product on your space of states. So you right away run into some difficulties. So we're not going to try to, well, unless we do a little string theory later on. I want to show you guys the standard model and stuff before we try and do something like strings. But it's, after a bit of this, it's not beyond you. You can canonically quantize a piece of string and then look for the states of various spins. So what I want to do, let's see, where was I? I was finding the conjugate momentum. So the point here is that we really need a functional derivative of something like this to properly extract the canonical momentum. So let's see how that goes. So we want to do this. Let's call the conjugate momentum pi, and suppose that is let's see. Well, the functional derivative of L with respect to phi dot, and that's the functional derivative of phi dot. And now it can be important to indicate what your parameters are, because in this integral, you're integrating over some of the parameters. You want to integrate over different ones than you differentiate with respect to. So we're taking a functional derivative of, all right, so what is this? This is minus phi dot squared of, let's say, y plus grad phi dot grad phi. I'm simply writing out this Lorentz product, d3x. Okay, so d3y. I want my parameters here to be y. So those are different derivatives. Those are gradients with respect to y. And now the second term here doesn't depend on phi dot. So what we need is minus del phi dot of phi dot squared of y with respect to phi x. Now, then we're going to integrate that over y. Let's pull the minus sign out. Okay, now this ends up looking just like an ordinary derivative. It would be nice if we keep the half with this, because we're going to get a 2. So if we define our Lagrangian and yeah, with a half. Never mind that minus sign. That doesn't matter. But now let's see. Any trick to doing this? Not really. You know, we get 2 phi dot as a result of that, but we're still left with the variation of one of these. So we get a 2, cancels the half. Then we're going to have a phi dot of y. And now we consider the variation of phi dot of y with respect to phi of x. We're going to integrate that over y. So what do we get? What is that variation? And you know, it seems like it ought to be, you know, something like 1 if x equals y, and something like 0 if x is not equal to y. Well, that's exactly what it is. It's a Dirac delta function. So our pi of x is now going to be, oh, geez, did I put the minus sign in here? We're doing it this way. This is another nice reason to use the minus the relativist metric. So let's just keep this positive. So pi will be positive. That's nicer. So we have a phi dot of y. And then this becomes del 3 of x minus y, d3y. And we integrate it and we get phi dot of x. And we're pretty happy with that. That just seems like what the conjugate momentum should look like, the time derivative of phi. So actually what this object is a momentum density. And you can follow through with units, but if you want to find the total momentum of the field, you have to add that up over all space, something like this. And that'll give you the entire momentum of the field. So now, having the conjugate momentum, we can write the Hamiltonian. And the Hamiltonian, everybody good here? All right. Yeah, like I said, you know, it really is pretty much like differentiation. As long as you keep track of where you need the Dirac delta functions, things work out pretty well. So what we're going to write is actually a Hamiltonian density. We're going to write phi dot minus the Lagrange density, where I guess I didn't find that the Lagrangian is the spatial integral of the Lagrange density. So this is your grad phi, and your phi dot squared stuff. So if we put this together, that's going to be a phi dot squared, and then the Lagrangian had a half phi dot squared minus grad phi dot grad phi, and lo and behold, let's see, what do we get? 1 minus 1/2 is still a half, and we get phi dot squared plus grad phi dot grad phi, and you see that notation was not idly introduced. That's Euclidean inner product like that. So, like I say, it comes up. So that's the Hamiltonian for our field. And what do we do with that next? That's the Hamiltonian density. The Hamiltonian is then the integral of the Hamiltonian density. Like that. And so the same as the relationship between the Lagrangian and the Lagrange density. What we get first is the Hamiltonian density and integrate it to find the full Hamiltonian. So now we can look at Poisson brackets. There's another time trick here, Guillermo. In field theory, in Minkowski space, we do equal time Poisson brackets and equal time commutation relations. So you consider two fields at the same time. Two fields at different times don't know about each other. So those would just commute. The brackets we're interested in are equal time Poisson brackets or equal time commutators. So let's see. Let me write our Hamiltonian somewhere where we have it. The Hamiltonian density is, d alpha phi. Not too hard to remember that. So.
Hey, Dr. Wheeler,
Yeah.
can I ask a question before you erase that bit?
Oh, yeah, sure, sorry.
No, that's okay. So we're integrating the density, the Hamiltonian density over spatial volume. Is there such a thing as like a temporal density?
Well, there's such a thing, right? I mean, the action is the U4x that is a full space-time density of some sort. So yeah. Let's see, what do you do with it? You break it in parts and work with parts actually. This is an awkwardness of the canonical quantization method because the Hamiltonian formalism separates time and space and really treats them as quite independent or sort of different kinds of things. It's not well adapted to relativity. And when you use it in relativistic theory, you very frequently find that the Hamiltonian vanishes identically as a result of, if you just compute it from the Lagrangian, the Hamiltonian can vanish. That makes it all relativistically invariant, but it's awkward to work with. There are ways around this. One thing that works is the path integral, right? So if I want to compute some transition amplitude between some configurations of my field. Can you guys see this? Sorry to be writing with the light blue, but yeah, let me know if you need me to use a darker marker. It's just the black is so messy. You write this as a functional integral over all field configurations of e to the minus I over h bar times the action functional of the field. And so it's a transition amplitude, and you have to square it to calculate probabilities and such, but it is a transition amplitude that the path integral computes. But notice this is fully relativistic. That can be an ordinary relativistic action, and we haven't necessarily separated out different pieces of space-time. Yeah. For quantum field theory and flat space-time, you don't have to worry so much about that. Now, Poisson brackets. The Poisson brackets. Oh gosh, let's see. Is this going to work? I want the Poisson bracket of our our field and our momentum at equal times. And how do you spell time? Poisson bracket, or peanut butter if you haven't had lunch yet. What's this going to be? Right, we're dealing densities here. This is going to be well, what would you normally get? You get like a Kronecker or something. You're going to get 1 if x equals y and 0 otherwise. Once again, it's a delta function. And I suppose you could write this with the delta of, t minus t prime. Let's see. That would extend it to all space-time, which would be nice. But the convention is to work with equal time commutators. Now, Hamilton's equations. The time rate of change of phi is given by, well, what is it? It's probably the functional derivative of the Hamiltonian with respect to pi x. And let's see, so that ought to be a functional derivative. Let's see, I'm just going to try this and see how it works. So the Hamiltonian is going to be a half d alpha by d alpha, no, not that. Whoops. Hamiltonian has to be written in terms of the momentum, right? So we're going to have a half pi squared plus a half grad phi dot grad phi. Okay, so it's a Euclidean sum because I've written that down, but the Hamiltonian has to be written in terms of the field and its conjugate momentum, not phi dot. So we get a pi squared here. So the thing that's going to be interesting here is the pi squared part. The grad phi squared is going to drop out, d3y. So now we come in, we're going to get a 2 pi times a delta. So we're going to have pi of y times del 3 of x minus y. And I'm pretty sure we're going to do all of this at some given time. And so we're just going to end up with pi of x when we do the integral and ln t. So let's see.
Can we adjust the screen, please? Screen check.
Oh, sorry. Thank you. Yes, screen check. We get phi dot equals pi. Cool, that worked. I'm always a little bit amazed that these things work right. So yeah, it's remembering rules is not my forte. So try writing something as a density and oh no, that doesn't work. So I write it as a function and something works or something doesn't. Anyway, let's go on with pi dot. Let's see if we can remember this. So if I want pi dot of x, that's going to be the partial of the Hamiltonian, functional derivative of the Hamiltonian with respect to phi. And now, right, the phi dependence is in this grad phi squared, so that's going to be the functional derivative phi of x of the integral of 1/2 grad phi dot grad phi, like that, d3y. So that was our phi dot here. So what happens? We go inside, we're going to get a 2, And what's it going to give us is grad phi. Then we have dot grad. We take the functional derivative of phi of y with respect to phi of x, and we get a delta function, 3y. The way we integrate over derivatives of the delta function is by integrating by parts. We're not going to worry about surface terms, so we'll get minus del squared of phi times del 3 of x minus y, d3y. And we integrate that, we get minus del squared of phi of x, where I have forgotten the minus sign in the very beginning, and so it makes it all probably plus. Okay, good. So does this make sense? So to make sense of it, I write, all right, phi dot is pi. So if I take another time derivative, phi double dot is pi dot is equal to del squared phi. And that's box phi equals 0. And we pat ourselves on the back because we did it right. And we know because we got the right answer. Okay, so there we are. We have written the Hamiltonian formulation of a massless Klein-Gordon field. And now, what do? We're going to quantize it. Canonical quantization. So we've got a Hamiltonian formulation. We just scroll down the page to remind me what I'm doing. Let's see. Okay, so yeah, canonically quantized. So our Poisson bracket is going to go to minus I over h bar times a commutator. All right, so we had the Poisson bracket of phi with pi as a three-dimensional delta like this. So that's going to become, right, minus I over h bar times the commutator, but I can bring those to the right, pi hat of y, t equals t prime, equal time. We get I h bar del 3 of x minus y. So straightforward canonical quantization, those are our fundamental Poisson brackets. And now we can, let's see, what do? We go ahead and now the time evolution of states is given by the commutator of the Hamiltonian with the fields. And we can generate all that same stuff, the time evolution. So first 2 or 3 lessons. Yeah, equal time commutators, but no, the function derivatives go to functional derivatives, just typically. Hamiltonia and Lagrangians go to integrals over Hamiltonian density, Lagrange density. Kroneckers turn into Dirac delta functions. So a few basic things, but mostly notational, and keeping track of whether you're talking about densities or not. One more big lesson. What did we just quantize? Phi of x goes to phi hat of x. The field is the dynamical variable. That's what becomes an operator. Just like the dynamical variables x and p of t become operators for a particle. So remembering that that x of t and p of t for a particle are the measurable properties of the particle, and fields are the measurable properties of a field theory, we end up quantizing the right thing. And as we'll see as we move to chapter 4. We just finished chapter 3. We're trucking along here. Chapter 4, which I haven't edited, but which is probably substantially correct, we can introduce a, well, Klein-Gordon fields. Let's look at Klein-Gordon fields. And there are two to consider, real and complex. So this goes along the same way, but the thing that we haven't defined yet in this little toy model is if phi is now an operator, what is the space of states? Now, phi is pretty clearly an operator, right? You can expand phi in Fourier modes and write a general solution. I suppose you guys did that last semester. Did you guys do that last semester? Yeah, okay. So you've, Tyler remembers it anyway, but yeah, okay.
We did it for the Klein-Gordon equation.
Yeah, okay. So yeah, we're gonna write that. We're gonna write E&M that way too, and Dirac. We're gonna expand all of these things in Fourier series because yes, we are in flat space-time and we can. You know, you have to work much harder in a curved space-time background to come up with a consistent set of states. If it's asymptotically flat, you can define things out there and maybe evolve them in. So if you've got really diffuse matter going back to past infinity and define your vacuum in something that's essentially flat, but the matter comes together and forms black holes and things, you can talk about that. Not going to talk about that. But it, yeah, but you guys, once you got a little quantum field theory under your belt, you know, read like Hawking's papers on black hole evaporation, because you can, you know, you've got an asymptotically past and asymptotic future vacua, right? And they're different, and that's the whole key. The vacuum state outside the black hole is different than the vacuum state at past infinity. You've got a unitary transformation that connects them, and you find that that mixes up your creation and annihilation operators and produces a thermal distribution at future infinity. Not terribly complicated ideas once you've got some of the basics for writing these quantum states. So, you know, in another month, go read that. You know, it's a good paper. You can understand it. Okay, let's see. I'm out of breath here. What are we going to do? Yeah, we're going to start quantizing sort of everything in sight. So just a list of future things. Let me see if green works any better. So we have a scalar field. Phi is going to be pretty much what we just did. D mu phi. Can you see this?
Yeah.
Thank you. All right. Let's see. And then, so a complex scalar, you don't need the half because one of these is the complex conjugate. And you know what? Here's a great exercise for you guys. Vary each one of these actions and find the field equations. Do you need practice varying field actions? Nah, no, don't need practice. All right, if that's tedious, don't bother. I mean, if it's tedious in the sense that you've done it 3,000 times and you don't need to do it again, don't worry about it. But right, with a complex scalar field, these are independent. You know, I mean, once upon a time I proved that to myself by writing out the real and imaginary parts, getting two real things, varying the real things, and checking that you get the same thing as if you vary phi star, vary phi independently. And that happens because the field equation is linear. And so it's pretty straightforward. So then we have a Dirac action. which we know now we can write as d slash minus m psi d4x. And then we have a Maxwell action where we square the Faraday tensor and integrate that d4x. Then it's interesting to couple that to sources. If you couple that to sources, you're going to have a quarter of this, because varying a in this gives a factor of 4. But then you also have a j mu a mu, which at first sight seems horribly non-gauge invariant. If I change a by a gradient, an additive gradient, this stays the same because it's the curl. The curl of the gradient goes away. What about here? You know, that adds a whole other term. But that whole other term is j mu d mu of your gauge change. Integrate by parts, that's a conserved current, and it vanishes. So this term actually is gauge invariant as long as J is a conserved current. You know enough gauge theory to know what I'm talking about. I haven't really talked about that, but E&M is one of the simplest gauge theories that we can talk about. If you want some basic, simple examples of gauge theories, look at I think it's chapter 10 in my gauge theory notes. You know, I devised some excruciatingly simple gauge theories there. You know, just like a rescaling of a simple X or something. Some things like that where you can see what's being done. But when we make a phase symmetry, a U1 symmetry, into a local symmetry, we have to introduce a gauge field to that. It's a connection on a U1 bundle for the high-minded. And connections always change inhomogeneously, and that inhomogeneous bit goes away in this term, so this term's okay. Now, in fundamental field theory, this J is going to be the current of some other field, some other fundamental field. It'll be the U1 Noether current of that field. So you can couple basically any complex field is gonna couple to electromagnetism. And we'll see that come out. We'll work through that after we've done the free field examples. Okay, and then of course there's gravity, and there the action is the Einstein-Hilbert action, and you guys have pretty much seen some relativity, right? Have you all seen relativity? You know, enough to recognize the, you know, I just wrote out the metric variation of this thing, and you know, if you actually derive the things you need to do it, like the variation of this volume element with respect to the metric, you know, that takes a good page. You know, it's long. And, you know, the longest parts of it, the variation of the Riemann curvature with respect to the metric, okay, that's second covariant derivatives and contributes at 0. Yeah, it took a few pages. I can send any of you that if you, yeah, send me an email if you want to see that. But it's in all the books, I think. Anyway, yeah, we're going to do all these except for the gravity one. Actually, yeah, that'd be a great midterm for you guys. Do linearized spin 2. You know, if you linearize the Riemann curvature, it's just an ordinary spin. There is such a thing as an ordinary spin 2 field. You know, something like d mu h alpha beta, d mu h alpha beta. You know, you could even give it a mass if you wanted. Something like that gives you a linear field equation. You can quantize that. That's not really a problem, I don't think. But yeah, the nonlinearity in general relativity makes it pretty hairy. Okay, so now, oh, I've stuck in a section here on functional differentiation. That's also in the gauge theory notes. And so what do I do about that? I think I've told you most of that, but yeah, let's see. Euler Lagrange equation. You want to see that for a field theory? Now this is all particle stuff. I must have stuck that in just as a primer on. Yeah, I haven't edited these notes yet. That's what I'm fussing with. Okay, so let's look again then at the scalar field. How are we doing? Good. The only thing that's going to be different here is all right, for this case. The only thing that's different is having the mass term, and it doesn't actually make much difference. It does not depend on the momentum. So we can pretty much just add it into what we've done. So the conjugate momentum is still going to be phi dot. The Hamiltonian density is going to be phi dot minus Lagrangian. And we know that that's pi squared. This is going to subtract half of that. And then it's minus the grad squared. So we get a half grad phi dot grad phi. And then let's see, is it going to be minus m squared? Phi squared, I think. Is that right? Yeah, looks like a minus.
1/2 is all you're missing on that one.
So simple modification there. And if we write the, oh, okay, I give you a bunch of exercises here. So let's see. So only one of you actually held up a list of exercises that you've done. So I assume the rest of you are failing. Is that true? So okay. So
Failing to remember to send you our list.
yeah. So I have received no lists in the mail. And let alone.
Did you get mine? I think I sent one.
Did you?
I thought I did. Maybe I didn't. Maybe I am failing.
Oh man. This is serious. Let's see. Yeah.
Forever ago. It was like 10 days ago now.
All right. So
It's like when you asked for it the first time.
You did. Oh, way back then. Let's see. Okay. So. All right. Well, I believe you. Let's see. Oh, here's.
In that case, I did all of them.
Homework.
Yeah,
I got lots of extra credit.
If you believe, then I sent mine too. Yeah.
Now, let's see. What is this one? Send you. Huh. Well, I don't know. Lots of emails, but anyway.
Maybe I'll send it again. Sorry.
Just tell me what you've done. I want to check that you guys are actually doing exercises. So actually do exercises. That's the crucial thing. And if you do have questions on any of them, bring them up and we'll talk about them. But
I did the first one of chapter 3, but I'm pretty sure that's like a one-liner.
yeah, a lot of them are, they're just to get you to write down the notation yourself sometimes.
Well, that reminds me, there's a typo in one of them in chapter 2. So maybe I'll try to remember that when I send it.
Yeah, especially send me any typos. I want to correct these notes. Okay, so anyway, I'm still going to be editing chapter 4 here, but I see 3 exercises. Find the field equation for the complex scalar field. Okay, so you know how to do that by taking the functional derivative of its action. That's what you're doing when you vary an action. You're just finding the first functional derivative. So you guys know how to do that. Let's see. Oh, yeah. Well, it's just what I thought. Find the field equations from those actions. So if you want a refresher, do that. But okay, so something a little more challenging that's a little more than just an exercise. Try and write the Hamiltonian formulation of one or more of those actions. Yeah, maybe work on the Hamiltonian formulation of the complex scalar field. We'll be getting to that soon. So why don't you guys do it? It's just like what we've done for the real scalar field, only you have to do it twice. So it's twice as much practice. Okay. All right. So yeah, let me see. Pi still comes out to be phi dot. No change there. The Hamiltonian, let's see, why is the Hamiltonian, oh, that's why. Okay, there's a sign. Yeah, I think we want a minus sign here, which makes that a plus. So we have a positive definite Hamiltonian. Now, let's see, if I vary this, the 2 goes away. I'm going to integrate by parts. I'm going to get a minus box phi minus m squared phi from this term equals 0. So that says box phi is minus m squared phi, which I think you probably know is minus m squared c squared over h bar squared phi if you put in h bar and c. But now the way to check this, right? This box is now a time derivative squared. And if I put in a plane wave like e to the I mc t over h bar, just a simple time oscillation, that's going to pull down an im, which is going to give minus m squared times this is phi times phi. That's the reason for the minus sign here, minus sign there, and ultimately the plus sign here. So it's because we're using that funny, the funny form of the Minkowski metric that we have a minus sign there. Okay, so did that go by in enough detail for you guys to get it? I said that all fairly fast. It's just a quick and dirty check on the signs. You can always write a simple harmonic solution to a wave equation and check the sign of your Klein-Gordon that way. Okay, Hamiltonian density is this thing with the half, that's right. Then Hamilton's equations do just what we just did, so nothing new there. The only difference is in pi dot. So the phi dot, we would feel really bad and hang our heads in shame if phi dot didn't come out to be pi dot, which is, or pi. Now, pi dot is going to be the derivative of h with respect to phi with a minus sign. And that's going to be, okay, right, we go inside the integral of this. We're going to get 2 of these and cancel the half. We're going to get 2 of those and cancel the half. This one integrates by parts. So what we end up with, this minus sign cancels the sign from the integration by parts. So we get del squared phi minus m squared phi here. And then when we look at pi dot is phi double dot, we recover box phi equals minus m squared phi, and it all checks. Everybody happy? Yeah, give you a minute. Kevin takes handwritten notes. You know, there have been studies that show that taking handwritten notes, you remember things better than just, reading and other forms. So good on you, Kevin. Let's see. So, all right, that worked. Now, quantization. We need the fundamental Poisson brackets. Those are going to be the same. We're still going to get pi is a direct delta. And so that's going to give us phi hat. Pi hat is IH bar when we quantize. So we've pretty much done all of this already. We just add the m squared. So let me see, where do we actually, all right, so there are Hamilton's equations, those work. So now, yeah, let's get into the nitty gritty here. What is the solution to this thing? And not too hard to write. We know that we can solve the Klein-Gordon equation with plane waves. So if we write something like phi is AE to the I over H bar P alpha X alpha, all right, then box phi is going to pull down, all right, two derivatives of this. We're going to get I over H bar P alpha squared times phi again. And the I squared is going to give us a minus. And then, let's see, what else is going to happen? We're going to get a P squared, but P squared is M squared C squared. I thought minus, but it's plus because funny metric, over H bar squared times phi. And so that solves the equation. Now, having those, we know that we can take a superposition. And I want to be a little bit careful here. Yeah, we're okay. We get a solution here. You know, we have P alpha is M squared, H bar C1. And this is E squared minus momentum squared. So solutions for the energy are plus or minus the square root of P squared. Well, we'll put the C squares back in. M squared C to the fourth. C's come and go pretty freely. You can always check your units. But basically, two energy solutions. And this is the thing that Schrodinger ran into. You know, everybody around 1920 knew to write something like the Klein-Gordon equation. But Schrodinger just took a non-relativistic limit of this thing and made it first order in time, because having positive and negative energies in quantum states leaves no stable solutions. Everything just decays into lower and lower negative energy states, and everything radiates away, which is not what we see happen. That was ultimately resolved by Feynman and Stuckelberg. But for now, let's just impose positivity of energy, not worry about those negative states just yet. So we can write a general solution as a Fourier superposition. Now I have to wonder why I've got this particular coefficient, but I guess it doesn't matter. So I'm going to write what I've got here. And I'm allowed to, because these A's, this A could depend on P. So I can write phi of X and T as over 2 pi to the 3/2. And again, I'm not certain why in this case I've chosen these coefficients without having looked over this in detail, but because these coefficients can depend on energy and momentum, I can stick any function of energy and momentum in I want. I want a root 2e. That'll give me a nice normalization eventually. And then we have A of P and E, the coefficient. So just imagine in this amplitude that I've pulled out, I could absorb that into this, and this is arbitrary anyway. So I'm allowed to put that root 2e there. The same with this prefactor. I could make that anything I like or absorb it into the notation. But then we have, let me check a sign here. I have H bar, P alpha, X alpha. And then add the conjugate, because my Klein-Gordon field is real here. Like this. But that doesn't solve the equation yet. I said I wanted to keep the energies positive, so I'm going to put a step function on the energy just to keep the energies positive for now. And then I need to impose the energy condition in order for this to actually satisfy our Klein-Gordon equation. So to do that, I put in a delta function of E, and since we've specified E to be, oh, well, let's see, now, let's just put the condition here, P alpha minus M squared. Now, you guys know what to do with the delta function of a function? You can always write something like this as a sum of delta functions, one at each root of the thing inside. So I can write this as delta of E minus P squared minus M squared plus, times some coefficient here, some coefficient delta of E plus P squared plus M squared. And in the current case where I've restricted the energies, that one's just going to go away. So this delta, this is nice for when we want to treat both positive and negative energies. But if we're only looking at positive, I could write this either way, and we've got what we want. Okay, and then a normalization, right? I want to integrate over all P, but I think I need something like a power of H bar to make this have the right units over H bar to the fourth. And once again, I'm setting C to 1 everywhere. So, all right, yeah, okay, now I see why I have this normalization. Okay, the delta function is going to kill the energy integral here. That's going to leave me with 3 Fourier transforms, and then I have a square root of 2 pi for each Fourier mode. So that's just the conventional Fourier coefficient. And let's see. So if you guys do not know this formula for delta functions, you sum over all roots of f. You have to normalize by the absolute value of f prime at the ith root times delta of x minus xi. So exercise, oh, it's in here. Prove that. If you have any questions on how to prove that, ask. But that's the next exercise. So you have to treat, the only thing you have to worry about is, right, f is some function, and if it's going through 0, falling or rising, you have to treat those cases separately. Just be careful about whether f prime is positive or negative, and you'll see the need for the absolute value here. Otherwise, it's pretty much just changing variables and integrating around each pole. So prove that. Now, oh, here's another exercise. Argue that that step function is Lorentz invariant. So I'll just let you wrestle with that. Okay, so now we do an integral over the delta function. So that's, well, it's gotten messy, but let me demess it a little bit. And that really is the general solution. All right, flat space-time. Yeah, I feel like I always have to say that because I'm so used to things being curved, but yeah, you know, field theory doesn't worry about that. Okay, so so we rewrite this, right? That's delta of e squared minus p squared minus m squared, I think. Yeah, that's right. And we can write that as what? Well, let's use our formula here. So we need 1 over the magnitude of the derivative. Think of this as a function of the energy. So f prime is just 2e. And we're going to restrict to positive e anyway. So I'm not going to need those absolute values. But the derivative is the same in either case, but I get a delta of e minus the square root, p squared plus m squared, plus a delta of e plus the square root, p squared plus m squared. And now when I substitute this into this equation, use the energy step function to eliminate that and eliminate the square root values. So this is all an aside, and I find phi of x and t equal to 1 over 2 pi to the 3/2. And now I see why I've chosen these various normalizations. This becomes just 2e, so I'm going to have d3p over h bar. Is it 34? How many h bars do I have? Oh, yeah, all right. So I've still got h bar to the 4th, but I'm going to change this to an integral over wave number and frequency eventually. So that'll clean that up. But then what I'm left with is I get a 1 over, well, I meant to put it down here, square root of 2e. And that normalization actually ends up being the right thing to do. And then we have a of now just p, because e is being specified by this delta function to be a function of p. So everywhere I write e, think e of p. And then we have e to the I over h bar p dot x minus e of p times t plus the complex conjugate like this. Can you all see it okay? Yeah. So now, let's see. So P over H bar is K, and E is H bar omega. So I'm going to go back and write this as a Fourier integral in. So E is H bar omega, which is going to depend on K, and P is H bar K. So I can write this as x of t, 1 over 2 pi. So this really ends up being a very tidy Fourier expansion. I k dot x minus omega t, where here you have to understand that the omega is a specific omega of k, like this, e to the minus I k dot x. No, wait a minute, does this become a minus, yeah, minus omega t. So we're making it real here. Okay, there we go. So that is now a three-dimensional integral giving us the solution to the ordinary Klein-Gordon equation. It's a simple linear equation. Now, the complexities in field theory really happen when you couple it to other fields. But the complexity for now is that we need to make all of this into operators. Well, the second complexity is running out of time. But let's see. To quantize, we're going to choose a time. And then there's a unitary time evolution to say what happens at later times. So the other thing we need before we can quantize is the momentum. But the momentum is just phi dot. And phi dot, you know, having both of these is what enables us to solve. So yeah, give me just a minute here. So pi of x and t is going to be, it's the same sort of thing here, but let's see, this is, oh, I'm sorry, that's not right. D3k, oh, I was looking at the wrong one, sorry. That was right, but it wasn't what I meant to be copying. So here, we need phi dot, so we're going to pull down a minus here and a plus there. And then we get an omega. So it looks to me just doing this off the board is, I don't know why we get a 2, but we're going to get a minus a e to the I times stuff. Let me just call that k alpha x alpha plus a conjugate of k e to the minus I k alpha x alpha, like that. So we get a relative sign between these two. If we do the inverse Fourier transform, we can solve for a and a conjugate. When we make these operators, the only way I can make phi into phi hat, there's no freedom here except to make a and a star into a hat and a star hat. Those will become creation and annihilation operators. And we're going to invert this Fourier transform, impose the canonical commutation relations on these guys, and infer what the commutation relations of a hat and a hat dagger are. And they're going to be like 1 or, well, maybe a Dirac delta. So that's for Wednesday. We ran out of time here. But I can hang around. I'll try and edit chapter 4. I haven't had a chance to look at that yet. But I did get a revision of a paper off last week, so life is good. Yes, I know. That always feels great. Now, if they just like the revisions, things are even better. Okay, so yeah, I'll stick around and answer questions. I've got time now. Yeah, all right, see you, Lyle. Eli, yeah. Just keep going on stuff. Keep computing things.
Yeah, I for the exercises for chapter 4, you mentioned that you wanted us to do something about like a Hamiltonian. I didn't quite catch that. Can you like say that one more time just so I know? Because I don't see that question here.
Yeah, all right, that wasn't in there, right? Yeah, so the ordinary stuff, but yeah, do the mimic everything I'm doing for the Klein-Gordon field for
Oh,
the
okay.
complex Klein-Gordon. So you're
The
basically
complex,
doing everything you just did it twice. So the
the current Klein-Gordon, right? Is that what it's called?
The-
No.
what's it called?
Charged Klein-Gordon.
Charged. There you go.
Yeah.
Thank you.
So complex fields coupled to electromagnetism, right? The action is real. So if you've got a complex field, you've got a complex conjugate multiplying it. So it's going to be invariant. The action's got to be real. What that means is that there will be a U1 symmetry to the action. So really any complex field that you're going to write down a sensible action for is going to have a U1 symmetry, and therefore it will couple to electromagnetism when you gauge it.
Mm-hmm.
And we'll do that, we'll do that with Dirac. We'll do that with the charged Klein-Gordon. So yeah, the action you can start with is d alpha phi conjugate d alpha phi plus m squared phi conjugate phi. And did we want a plus or minus here? Figure out the sign on that. But yeah, so if I vary this guy, integrate by parts, I get a minus. So I think I need minus there, but it's the same as the other one was. So just work through all of this with the complex case. Okay, good.
Thank you.
Yeah.
Have a good
Other
day.
questions are coming? Okay, see you, Guillermo.
So when you said that it can couple to a complex field, is there an inverse to that it can only couple to a field that can be complexified, or that it can only couple to a section of some type of field?
Yeah, electromagnetism will not couple to a real field because there's no U1 symmetry. So the critical thing for coupling to electromagnetism is that there's a U1 symmetry.
Thanks again.
For the field action.
Heading out. So.
Okay, see you, Tyler.
So does it only couple to like the U1 section of a larger field? Like in the Dirac field, is there a section that the E&M field does couple to?
The Dirac field is complex, so it coupled to E&M. Now, if you have like a Majorana field, that's a real Dirac field. Okay. Then you would have restricted it to where, let's see what'll happen. Yeah, you won't have, you've canceled half the fields and they're real, so those won't couple to E&M.
Right.
Yeah. So yeah, the whole question is whether your field has a U1 symmetry.
Yeah, and I guess what I'm asking is, does the E&M part couple to like a certain form of like, so in the Dirac field, is there, I guess I'm looking for the coupling measure. Like is it coupling to an inner product so that it looks like a C scalar and then it's being fed into the E&M field? That's yeah. Okay.
The way it couples, the way that E&M provides potentials, if you like, for say the Dirac field or any kind of complex field, is you write a U1 covariant derivative. So we're going to replace all the partials by U1 covariant derivatives. And that brings in the U1 connection, which is the vector potential. So now the Dirac equation is going to depend on some products of the vector potential and the Dirac field. On the other hand, you also get a source for electromagnetism, because when you vary A to get the Maxwell equations, it's going to be in that covariant derivative. And what you find as the source for the Maxwell equations is the Noether current for the U1 symmetry. That's all very tightly wrapped up.
Yeah. Oh, that. Okay. Okay. Yeah. Okay.
Symmetry
Yeah.
is just totally central to the whole thing.
Yeah. They're all getting coupled to their no-third currents, right?
That's right. That's right.
So
It works for other gauge freedom too. So if you have like 3 spinor fields coupled by SU3, right, you're going to introduce a bunch of connection forms, and those are gluons.
true.
All right. So we'll see all that. We're going to do all that.
Okay. Okay. Cool. Yeah, I think that's about all I had. So
Okay. All right.
yeah. Okay. I think going forward, I'm trying to put like kind of the index notation together with this type of field theory, because there's something to do with this raising and lowering that is somewhat trivial with the metric, but I guess to see the Dirac field straight in in a curved space-time with the that's I guess an equation I'd like to be able to understand.
Yeah,
Here.
we're going to be doing a lot with Dirac.
Okay.
You know, solving the free Dirac equation is non-trivial. I mean, it's still a Fourier transform, but you also have this whole matrix thing going on with the Clifford algebra. So you have to come up with a basis for, you know, 4 spinors, right? So you need a base you need 4 independent solutions. You're going to take linear combinations of all of those as well as the Fourier series. So, you know, there's a bit to work out with that. Yeah, if you're wondering about Dirac fields in curved space-time, the coupling is in the gamma matrices. What you do is you define, you use the solder form, right? An orthonormal frame field. And that connects like a gamma mu to a gamma A, where A is orthonormal, and those are your ordinary Clifford algebra guys. And a gamma mu has the components of a solder form in it, basically the metric in mixed spaces. And so a metric variation is going to get you an energy tensor out of it.
Okay, yeah, that makes sense.
So you'll have a source for gravity there.
Cool. Yeah, I guess the hard one for me is still, but I feel like I'm making progress, is viewing how the dual space is factoring into all of the index notation, I guess. Like because there's 2 dual spaces that we get, and in our class the metric dual space will be trivial because it's Lorentz, and then in the GR the field dual space will be trivial because we're all just doing scalar particles. So I'm trying to fit those 2 dualities together, like basically taking a transpose is kind of like the field duality, but it'll be a conjugate transpose, and then the raising and lowering is like the space-time duality. So I can kind of see that you're going to end up getting like transposes like smashed together if you write everything out in matrix form. Like if you want to, okay.
Yeah. Okay. Yeah. Well, actually, yeah, that's interesting because you do get, well, when you have a path integral, it's a transition amplitude. You're going to take the square of that. So when you square it all, it actually does put your field operator right next to the dagger field operator as an outer product. And that becomes an operator that you can expand in gamma matrices.
Yeah. Okay. Yeah.
So,
I think
so. Yeah. So there are a lot of tricks with the Clifford algebra stuff that make it straightforward but complicated writing out. QED stuff. Yeah. So yeah, you always ask me about duals and Fock spaces. Let's see. I don't use those concepts very much. They're there. Certainly Fock space is the space where the whole thing lives, right? So, no harm in, having that in mind, right? Yeah. But, the times you actually need to worry about it, you're looking at the scattering of, an electron and a positron into electron, a positron, and a photon. So yeah, okay, it's like you know, up to the third 3 particles in Fock space. Or quarks, you know, you use some combination of Young tableau and what are they? What are these called? These diagrams. I just lost the name. Weight diagrams from group theory. This Lichtenberg book goes into them nicely, but you know, so you use a few things, but you know, okay, you're taking either quark anti-quark pairs, like a 3 times a 3, or you're taking quark 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 pairs, which is a 3 times 3 times 3, and you get an octet and a decaplet and a singlet, and you know, that's all the bigger in Fock space you go. Well, okay, so in a proton, you've got 3 quarks and you've got a mess of gluons. So, you know, I mean, who cares that you live in Fock space? You just want to model it.
You're right.
So I really, you know, never really touch on that idea
Yeah.
in any way I've found useful in this kind of stuff I do. Now, you know, if you're really interested in formal results in quantum theory, yeah, you may want to talk about Fock space. For duals, yeah, there, you know, any vector space has a dual space, you know, and it may or may not be the best way to think about it. You know, for the Bra-Ket stuff that we introduced today, yeah, that's the dual space, and that's actually nice to know. In space-time, the dual space on a manifold, I prefer not to think of as the linear mappings on a vector space. I like to construct the 2 vector spaces independently, right? Because they have an existence that precedes any kind of linear mapping or product between them, right? You can define forms as linear maps on curves. You can define tangent vectors as, you know, tangent vectors to curves or equivalence classes of such. And each of those relies only on having a manifold, functions on the manifold, and curves on the manifold.
Yeah.
So you don't need any idea of duality until after you've built those, and then the fundamental theorem of calculus is your duality. It's really nice. So there, you know, I guess it's because I work in differential forms all the time. You know, they're just so efficient that I get annoyed when people define them as linear maps, because they form a vector space. It's a perfectly good vector space. Why does my vector space have to be maps on your vector space?
Yeah.
So
I want to be the vector space.
Yeah.
That's
All
my
right.
turn.
So anyway, that's a personal preference, you know, when it comes to manifolds and stuff.
Yeah, but I kind of get the point. The point being that on a manifold, you're more defining, like you say, like smooth curves or fields on it. So it's not strictly a vector space until you turn that object into a vector space, like the vector space of curves from this point. So at that point, you might as well just define the dual space as like the integral, the curve length integral or something. Is that what I'm viewing as? Is that the dual space, you're taking it maybe not in a canonical vector space idea, just more of a space of linear maps?
Gosh, let's see. So yeah, we could do the space of linear maps. Let me think how I define these things.
I'm sorry.
No, that's okay. All right, so that's kind of cool, huh? You know, we got.
I think so.
Fourier stuff. Okay, so now we're just going to put hats on everything,
right?
Okay,
and make it canonical.
And yeah, so it's clear that what we do is put hats on things. You know, it's funny. It's only after we define the operators that we're able to say what space they act on. Isn't that weird?
Yeah.
You know, but you use the commutation properties of the operators. Just getting squirreled here, but you use the commutation relations of the operators to then calculate properties of the vector space they can act on. And you find, oh, I can define in some sense, a lowest state, and raise from that and define a complete basis for my space of states. You know, it's a little like finding all representations of the rotation group. You characterize rotations by the rotational Lie algebra. You know, Gij is epsilon ij k gk, right? And then you find all ways to represent that group, linear representations of that group. And you find there's one of every dimension just by manipulating the properties of the operators. So it's sort of backwards, doesn't it seem like? I mean, yeah, you know, I could have a space and ask for the, you know, a vector space and ask for linear operators on that space. Mm-hmm. But here we're doing it very typically the other way around. We have these operators that satisfy a certain relationship, and then we go find all representations. We find all vector spaces that those can act on.
Yeah, like almost we're building it out of the eigenvectors of the operator itself or something. Like as opposed to saying it. Or
even finding the right operators to find the eigenvectors of to build it. But that's right. That's what we do. Yeah. So
that is weird because they're defining the space. Yeah. And then
that worried me when I was writing down, you know, like basically the fundamental properties of quantum theory. Well, or canonical quantization. So what do you need? Well, you're going to change Poisson brackets into commutators. Cool. Now you've got operators, but you haven't defined what space they act on.
Yeah.
And so I felt like, oh, so you need a vector space. But you know, that's not really where you start, in fact.
Mm-hmm. Yeah.
That ends up being the probably the biggest challenge in quantum gravity is defining your space of states. You know, like, what are those? Anyway, I was kind of defining some vector fields. So if we've got a manifold, we have two kinds of objects. We can have mappings of the reals into the manifold, and we can have functions that map from the manifold to the reals.
Yes.
And it's really a pretty elementary manifold that wouldn't have those properties. And we've got charts on everything, so we can write it all in terms of charts. But basically, one thing you can do is you define, you've got a curve, you can define linear maps on the curve. So a linear map on the curve by linearity can be broken up. And what it's going to do is, it's going to take, you can add up little pieces of the curve, and what the map does for each of those. And if I call what it does for each little dx, something like that, and then add them up, I'm doing an integral. And those are the components of my vector. So linear maps on curves can always be written as integrals, and whatever is inside the integral is your one form. It is a vector. The other thing you can do is you can you can look at how a function is changing along a curve.
Sure.
This is sort of a Lie derivative, right? So you have if this is C of lambda, right? So you've got some parameter. This is your parameter along the curve. So I can find how that function is changing with lambda, and that gives me my tangent vectors. And if I write those in the chart, now I've got components of those guys. So these guys expand in a chart as some linear combination of your chart coordinates, and these guys always expand as in terms of some differentials. And if you put these two together, you're taking dd lambda of this, this is dx d lambda d lambda, dd lambda of that gives you, what is it, omega v. But I don't know, somehow, if you're careful writing this all down, that turns into the fundamental theorem of calculus.
Sure,
Yeah,
sure.
you're differentiating that function and you're integrating that function, and you come out with that function.
And then in this interpretation of duality, the dimensionality of the space is kind of like is it these omega i's? You said like these are the components. It's like how many segments you would break it up.
I runs from one to what the dimension is. Yeah, it doesn't matter what the dimension is.
And in fact, it doesn't even have a set dimension, right? It has
now, definition of a manifold has a single dimension over the whole thing. So your charts map you into Rn for the same n at every chart.
I guess I mean for the dual space here, if you broke it up into 10 parts, it would be a 10-dimensional dual that you're taking or something. I guess the WI's.
You're breaking this into infinitesimal parts, which I'm writing as dx.
Yeah. Okay.
Okay. It's
an infinite dimension.
The number of parts is infinite, but when you put it in a chart, the range of I here is over the dimension of Rn, whatever your chart's mapping into.
Okay, I was viewing it more as the Riemannian sum limit, and then seeing it that the dimensions of V were increasing as you went to the limit. But this dual space it's got like, well, I mean, like you're saying, the vector space duality is given by the manifold, but like this integral is in some ways, that's, I guess, the idea is what type of duality, because this does seem like a different type of duality than just your usual like Graham-Schmidt in through a finite dimensional, taking it to a, do you see what I'm asking? Like just that, like how you what's got me going is that you started saying that like these, and maybe this is just a misnomer, but I was taking that we were breaking this measure of this curve up into segments, right? And then adding together just as the usual integral limit.
No, that's right. That's right.
Is the duality the entire? Is there a slightly less infinitesimal notion of duality from this? I guess like if I took this is a bad question, I think, because our curves will always add because it's linear, so this is always just in it. I understand this from the manifold perspective, because then your dual space is like your tangent space of sorts, but it's going to be like point parameterized.
Yeah, well, yeah, the space of all these guys are take an equivalence class of these guys, and that's your tangent space. Take equivalence classes of these, and that's going to be your cotangent space.
Okay.
There are two vector spaces at each point of space-time of a manifold, any manifold.
Okay, and this is the sense of duality in general relativity, kind of, right? Or in just
I'm trying to think if I can. Let me try to make this more precise. I don't know if I can. I've done this nicely once or twice. Maybe I can.
The gauge theory went through it pretty good. This is all making a lot of sense because of that. I think you mentioned this in here, but no, go ahead. I'm sorry. Yeah.
Yeah. So we've got these maps into curves. We also have charts into Rn. Lots of high dimension Rn. Those are all perpendicular. Right. So we're in some region here. So we've got some kind of coordinates. So this is just putting labels on all the points here, so we know where we are. And so if I have let's say I have a linear map on a curve. So let's let omega be a map on the curve. And since it's linear, let's see, I can write this as a sum of a lot of little pieces. And let's see, so if I'm at some place lambda, yeah, I'm trying to think how we do this. So I want to look at.
You could index lambda, but no, sorry.
Yeah, so this is lambda down here. So this is parameterized, but if I act on C of lambda with my chart, that basically gives the curve as some xi of lambda, right? That's what my chart does for me. It puts labels on these points. And then linearity of this map. So this is mapping the curve into the reals. And yeah, so what I can do is write that, right? So if I'm thinking of that as omega of xi of lambda, I can think of a small change in this as omega of x of lambda plus d lambda minus omega of x of lambda, and that's just d omega d, or what? That's d omega dx, dx d lambda, d lambda.
D lambda. Yep.
Yeah. So it's a differential here. So I multiply and divide by d lambda, and I'm going to add all those things up, and in the limit that becomes an integral of d omega, which is written as omega I dxi along the curve. So, so my mapping on the curve, my linear mapping on the curve, can always be written as an integral along the curve. Mm-hmm. And when I take linear combinations of these, I can get linear combinations of derivatives. So I don't need that derivative in there ultimately. I can form more general forms than just gradients. Now for a tangent vector, certainly df d lambda has a clear meaning, but I can write this as an abstract directional derivative. If I leave off the f, I can write this as in a chart. This becomes dxi d lambda ddxi. All acting on any function I like, but the function I'm acting on doesn't matter so much as the fact that the change in my chart as I change lambda gives me the components of a tangent vector.
Sure. Yep. Mm-hmm.
And then let's see if I, so this integral is the integral of, basically the differential of a function written as df d lambda, and this directional derivative is d lambda. So if I take a tangent vector to the linear map, I'm just gonna end up with the function f, I think, if I did that right. Did I do that right?
Yeah,
I almost did that right.
The idea that you'll get just that they're already canonically dual, so you'll get a delta.
They're already dual, in that sense. So taking Yeah, taking a tangent vector to the linear map on curves gives me the function back. And it's so it's the fundamental theorem of calculus that tells me that if I have some one form and I have some tangent vector, that the result of that is something that exists a priori.
Yeah. So presumably there's a way to do this. Like, is this what we're actually doing in gauge theory, just with this derivative being the covariant derivative? Is the same idea, the actual duality?
No, those aren't quite that close. Yeah, to define a covariant derivative, right? You know, all of the stuff that you use in relativity is stuff you add on to a manifold. So, you know, you have this basic structure. You have a couple of vector spaces associated with each point, but then the thing you do is you can add two different structures to the whole thing. You can add a metric so that you can, you know what infinitesimal distances between points are. And that can give a special mapping between the two vector spaces. So you can use that. You can use that to make your to relate vector spaces, or to give you lengths of vectors or lengths of forms. You can use the metric in a lot of different ways like that. The other structure, independent of that, is a connection. You can add a local general linear transformation if you're looking at coordinate invariance, or if you want to use orthonormal frames, a local Lorentz or local orthogonal transformation to relate infinitesimally close tangent spaces. So it's directly a map relating these vector spaces at nearby points. And between those, you can construct the idea of geodesics and curvature and all of that. But those are structures you add on top of the manifold. Yeah, a manifold really only tells you about connectivity. You know, it's let's see. I don't have any simple shapes here. You know, a teacup and a donut are the same thing, right? So yeah, so it's just topological. It's the metric and the connection that add the kind of structure that we think of as really specifying a particular shape.
And in general, then every gauge group doesn't have a metric necessarily, but they all will admit connections.
Yeah.
One way to say it.
The Maurer-Cartan equation describes the connection on a Lie group. So yeah, you've always got the Maurer-Cartan connection, and you can generalize it if you want and curve that space. The what was it you just asked? So yeah, a metric. Well, Lie groups often have a metric, but right, semi-simple Lie groups have a metric, the killing form. The killing form is non-degenerate on semi-simple Lie groups. And so you can use that as a metric on the Lie group, on the Lie algebra.
Yeah, okay. That's, I think, what I'm trying to get at is that's what I'm trying to dig at is what is a metric for a Lie group? And then the verse is I'm trying to see what the Lie group of a metric looks like. Trying to see both ways.
Oh, yeah, different question, right? So yeah, the Lie group of a metric sounds like you're asking about symmetry. The symmetry of a given spacetime.
Mm-hmm.
So that would be the set of vectors psi such that the Lie derivative of the metric vanishes in the psi direction. That gives you the set of symmetries on a space-time with metric G. Now the metric of a Lie group. So if I've got a Lie group, I can find a Lie algebra.
Yeah.
And if I take the trace of the product of a couple of generators, that's called the killing form. And in a semi-simple or simple Lie group, that's non-degenerate. If it's non-degenerate, you can take it as a metric on this vector space. The Lie algebra is a vector space, so you can use it as a metric there.
There we go. Wait, can you say that just one more time? There we go. That's brilliant.
Yeah. So given the Lie group, I can find the Lie algebra.
Yes.
Given the Lie algebra, I can take the trace of the product of any two generators, and that's a necessarily symmetric form. Maybe degenerate, maybe not. In fact, it is non-degenerate exactly when your group is semi-simple or simple. And in those cases, which are really the ones we're dealing with, you can use this as a metric on the Lie algebra. The Lie algebra is first and foremost a vector space. So
it is actually
the generators form a basis. So the elements of your Lie algebra are linear combinations of generators. Right. So this is your Lie algebra, those guys.
Uh-huh.
Right. So you take the trace of a basis. If it's non-degenerate, then I can ask about Kij, Vi, Vj.
Sure. And that just looks like the outer product of the geodesic vectors, right? I mean, this trace.
Oh. Yeah, I don't know, maybe.
Maybe it's right,
yeah,
but okay, this is so cool.
In an adjunct representation, all right, G, all right, one representation for a Lie group is given by the structure constants, like this.
Mm-hmm.
So matrix components of the ith generator, I can take to be these.
Oh, I forgot this.
Then if I take Gi, K, M, G, J, M, N, that's going to be C, what is this, K, I, M, C in this representation, M, J, N. K can be written in terms of the structure constants of the group.
Cool. Uh-huh.
So once you've written the Lie algebra, it's not too hard to find out whether it's got a non-degenerate killing metric. So the Poincare group does not. The killing metric of the Poincare group is degenerate. The killing metric of the conformal group is non-degenerate. And so that actually gives you a priori an inner product on the Lie algebra.
Mm-hmm. Okay. Okay, I'm kind of seeing how this construction is working.
Good.
More than.
Good.
Do you remember the killing theorem? Do you remember off the top of your head what the basis theorem was? I can search for it too.
Wait, the base, are you talking about this or the Lie?
Yeah, the killing for probably the if and only if on the trace.
On the trace. Oh, this?
Yeah.
Okay, this is non-degenerate. If and only if the group is semi-simple.
Okay. That's where I'll go dig with that theorem then. You know, I'll just it doesn't have a name or anything, eh?
Oh, it's just one characterization of semi-simple groups, I think.
Okay.
There are several ways to tell what you mean by a simple group or a semi-simple.
Yeah.
And that's one easy way to figure it out if you don't already know. Unitary groups are simple. There's a classification of simple groups, right? So they're orthogonal and unitary, general linear, special linear, symplectic, and then there are 5 special ones or something, right? Exception. Is that the word? Exceptional groups?
I think so.
Yeah, those guys. You know, E8 and those guys.
Yeah.
Yeah. So there's just a simple list of all of the simple groups, and then semi-simple groups. I guess they can be products of those for the semi-simple groups. But the Poincare is not, because all of the translations commute with one another. The conformal group is a simple group because you have 2 sets of translations, and while the P's commute with the P's and the K's with the K's, the P's and K's don't commute. And so they make that full 2n dimensional matrix non-degenerate.
Mm-hmm.
Which is why there's a natural metric on biconformal spaces.
Yeah, see, I think that's the picture that I'm subconsciously trying to grab at, is what's enough to give like what do you have to embed any of these field theories that were these groups of these field theories in to actually realize them as continuous metric. I'm trying to picture a manifold with some of these other and so this is good to dig at this. I forgot about this killing form basis thing. So because that's super a connection between the two. So
Good.
Thanks, Professor.
Oh, you bet.
Okay.
All right. Yeah. I'll see you Wednesday, if not before.
Absolutely. Wednesday. Yeah. And I don't know if you want me to still set up a Zoom chat independent of this, or
Anytime you like. I mean, we talk plenty, so I sort of know where you're coming from.
okay. Yeah, me too. I
I'm
always
not-
like
I'm not
talking
worried
more,
about
but
it. But yeah, if you want to meet anytime, I'm fine with that.
okay, cool. Yeah, I like meeting as much as possible, but
Yeah.
we talk a lot, and but I also want an A, so I don't want to. Oops, she didn't show up for her special meeting.
Oh, well, yeah, that's I wouldn't worry about grades. Just keep being fascinated with physics, and it's going to be clear that you're getting stuff or not.
Okay.
Yeah, basically I want to set up these individual Zooms, mostly touch base with people, make sure they're doing all right. You're doing all right. I'm not worried about that.
Okay.
So, anytime, if you've got a question and you want to talk, we can set up a Zoom.
Okay. Yeah, I'm sure I'll check out the problems and we'll see where that takes us.
Okay. All right.
Cool.
I'll see you, Alex. Have a
Have
good
a
day.
nice day, Professor.
Bye.